Hello friends, today's session is about the introduction to blockchains. In this session we will talk about all of the different building blocks of blockchain technology. We will also try to understand the relevance of blockchain technology and why it is important compared to some of the legacy systems. With this introduction, we will be able to understand how blockchains compete with all of the different systems that offer features similar to blockchains, and at the same time we will try to see how three different diverse technologies come together to offer the proposition of blockchains. One of the things that I have always found very easy to understand when we talk about blockchains is how similar they are to banks, and also from a technology standpoint how similar they are to a normal database. Our analogy of the bank is going to make our understanding of the relevance of blockchains very easy. The reason why banks are easy to understand is because everyone has had a relationship with a bank in some form or the other. Most of the times we have a saving account in a bank and we interact with the bank through various different channels, like which could be an ATM or going to a branch or talking to a banking agent on phone, but in the end we are essentially interacting with that savings account which is a part of the bank. If we remove all of what happens in the bank around all of the branches, ATMs and all the systems that are maintained around credits, finance, interest, then at the heart of the bank what we can understand is there exists a ledger. A ledger is very similar to a database. If you think about it, whenever you open an account with the bank, what the bank does is that it creates an entry in this ledger. This entry has your account number, some details about you, and your opening balance. From then on, whatever transactions you make with the bank, this ledger gets updated with those transactions. These transactions are what represent your activities or your interactions with the bank that result in some sort of movement of money. At a high level, this movement of money could be a deposit, a withdrawal, or a transfer. And all of these different types of activities create entries in this specific ledger. Now, expanding our discussion around banking, one thing that we need to understand is that banks need a lot of legislation, and that legislation is primarily there to ensure the safety of our deposits. There are instances of numerous legislations that are there in different countries. For example, America has the Banking Act of 1993, which was created by the Federal Deposit Insurance Corporation, or FDIC. This act is still followed by banks in the US. India has the Banking Regulation Act of 1949, which is very similar, as it controls all the banks. What also needs to be understood is modern banking needs a lot of IT support, and all of that IT support is essentially needed for securing that online ledger. Now, what we mean by this is most of the times banks maintain that ledger on a database system. It's obvious that when you have a database system that's as important as carrying your deposits, you need a lot of security around that. You need to control the access to that data system. You need to ensure that the data is maintained redundantly you have to ensure that data is available all the time, and then there is a level of resiliency in the systems that maintain that data. So all of this IT support is maintained by banks for primarily securing that single entity called the ledger that has your transaction activities. So if you think about it, your deposits, which constitute of all the entries that are there in the ledger, they are the core of that bank. And this bank uses those deposits in different forms, like using it for lending money to others, charging you service fee on that deposit, also using that deposit in stock trading to earn itself money. All these three and some of the other means are how banks make money. But that money is made by using the deposits that are aggregates of all the saving account balances that are there in a specific bank. Now let's come back to the concept of trust. What happens is that banks have to maintain a level of trust so that people can continue to deposit money in banks with the insurance or with the assurance that this money is always secure. What we mean by this security is that this specific ledger on which entries are maintained is always secure. It is a proof that you deposited some money in the bank or you transferred some money from your account to someone else's account in a bank, and all of the amounts and the times that were involved, they were always secured. All of what we said around legislation and IT support primarily maintains this banking trust, or the trust that your money is never going to be destroyed, your money is never going to be tampered with. And the way that security is maintained is by securing this specific ledger. What banks ensure is that no one should be able to tamper this deposits data. No one should be able to damage this data, or there should not be ever any inconsistency in this ledger. Banks also go through a lot of audits, and this ledger has to be always open for audits. All of the transactions that are made on the ledger, they should be transparent. Anyone should be able to verify how his balance was changed as a result of a transfer. So all of these different security measures are what ensures that banking trust. And one of the things that one needs to understand is that since banks are just entities, then all of the legislation, all of the audits, all of the monitoring that goes into a specific bank operations are primarily geared towards creating this trust for the end user. Before we move ahead, now we have to make an assumption that this specific ledger on which the entire banking operation depends is actually a database system. That's not a difficult assumption to make because all of the modern banking is IT driven, and it would be really difficult to maintain that banking and its operations on paper copies. It has to be a database system with a popular database vendor like possibly Oracle or MySQL or MS SQL. With that assumption, what we have to now concentrate on is that with such a database system, what are some of the challenges that might occur, or some of the problems that might manifest themselves if the system is run on a database. To do that, first we have to understand what is a database. A database is a combination of a database management system and the actual data that is run on a file system. So me or any developer who's a user communicates through a database management system or DBMS layer to the database that resides behind it. And as a part of that interaction, I have to first create an authenticated session or a username password driven session with DBMS, which manipulates, adds, or changes data as I operate it. Most of the times, this data is maintained as an RDBMS system or a relational system. What is meant by relational system is that it's maintained in tables. In the simplest form, a relation is called a table. What we mean by a table is that there is a relation maintained between different columns or different attributes that are grouped together to form a record. If we think about a simple table creating a relationship between the city, the age, and the salary of an individual, then it's going to look something like what's shown on the screen. So this, for our purpose, is a database system. We'll not go further and define database systems in detail because this is going to be enough to understand some of the problems that we are going to talk about, especially related to database systems in the coming slides. One of the things that a database system has to do is to maintain an authentication. What is meant by that is I have to log into a database system to make any updates to the data, to retrieve data, and to change data, models, even delete data, or whatever I want to do. And the authentication or credentials, they are maintained in the database system itself. So if I have to change the username and password, then I have to actually get into the database and change it from inside the database. This is something that's called self-controlled updates or self-managed authentications. This is not a problem per se, and it's obvious that something like this would be a part of the database system, but some of this introduces some challenges that we are going to talk about later on in our discussions. The other problem with databases is that databases can crash. And that's not to say that the software can crash. It's possible that the hardware that hosts that database system software can also crash. There could be a number of reasons that can be beyond someone's control that could result in this crash. So it could be a natural disaster that crashes the data center that's maintaining this database. It could be a power failure. It could be a physical damage to the device that's maintaining this data. A number of reasons that could cause the same outcome, that is a crash. This is again not a problem just with databases, but any IT system can face this problem, but it exists nonetheless. These are just two problems that we've discussed. There are some other problems with the database, but they exist with some of the legacy systems as well. One of the things that we ensure with a bank ledger is that all the security and authorization that needs to be there before someone makes change to the data. So when I talk about my account statement, there is a lot of authentication that needs to be done before I am able to withdraw money from my account. If I am in the bank branch, that authentication is verifying my signature on the check leaf. If I am interacting with the bank online, then it's my username and password, and in some cases my one-time password through my cell phone or email service provider. All of these are set up to ensure authentication and authorization. Now imagine a database that's able to maintain this authorization automatically, and at the same time that same database giving me all of the trust that the bank does today. The trust that is available by the bank is not the result of the database. It is the result of all the legislation, all the monitoring, all of the IT staff, all of the redundant data centers that are maintained by the bank to ensure that my data is always secure. But what if I'm able to conceptualize a special kind of ledger or a special kind of database that's able to do it on its own? What that means is, if assuming that a bank maintains my database on Oracle, and by some means Oracle itself can say that you don't have to maintain any IT support, because the way Oracle is structured is that it can never crash. The way Oracle is structured is that no one without authority can make any updates to the data, or remove any data, or corrupt any data, or tamper with any data. What that means is that I am able to create a ledger that's very suitable to a bank. In fact, that can replace a bank altogether. So we have to hang on and think about that for a bit. What I'm saying is that I am offering, or I am imagining, a database system that's self-trustworthy. The technology inside that database ensures that it cannot be damaged, it cannot be tampered with, it cannot be corrupted, and no one can steal it. I'm not saying how that's going to be done. I'm not talking about the technology. I'm just saying that imagine if there is a database like that, then I can effectively replace the entire banking operation and just put that database in its place. Because all we need from the bank is the trust. If that trust can be offered by the database system, then we don't really need a bank to maintain that trust. We don't need the legislation, we don't need the audits, we don't need anything. All we need is the instance of the database running, helping us maintain our accounts. Now this is something interesting and far-reaching, and if someone is able to create a ledger like this, then it's going to be in direct competition with the banking industry. Today, as we saw a couple of slides back, bank earns a lot of money based on the deposits that we make in the bank. If we are able to keep track of those deposits in this ledger and not go to the bank, then the bank loses a lot of business, which is why Bitcoin, which is a blockchain that kind of tries to replace bank, is in direct competition with banking systems. So carrying on our argument around what needs to be there in this ledger, if we talk about a banking ledger, what we can be sure of is that it looks something like this, which is going to be essentially a record of all the entries that represent a deposit or a withdrawal or a transfer. If you think about it, these are essentially the three activities that you can do. There isn't a fourth one. You would either be putting money in your account, removing money from it, or transferring it. And your ledger just needs to capture that with the amount and the timestamp or the date. So if you think about it, your ledger is a very, very simple chronological record of your transactions. Now that we have established what our ledger looks like, we can take a look at how we can structure this ledger, which is essentially the starting point of our alternate technology or alternate ledger that we've been trying to visualize, that can offer all of the promises that the bank can offer. Now, one of the things that we have to assume at this point is, since we are talking about blockchains, that ledger that we were trying to replace is essentially the new blockchain ledger. And we've been using the word ledger for a while, which is essentially an accounting term, but for our purposes, we can use the word ledger with database or with blockchains. A ledger is essentially a set of entries or a set of transactions that are recorded that represent someone's financial activity. And that's essentially what we will do when we will try to translate the ledger or the database that we've been looking at from banking perspective till now to the new blockchain type of ledger. Now imagine that we have this ledger that's maintained by the bank, which is essentially having, assuming for simplicity, just one branch. Then this ledger could be a group of all the entries that are made during one day. As a part of its operation, during one day, a bank is going to have a lot of transactions that are going to come in from different sources, which could be online transactions, transactions made by people who walk into the branch, transactions made by people who submit checks that come into the branch, and all of those form the entire set of activities that are recorded on the ledger. Now, in our effort to convert this ledger to a blockchain ledger, what we do is we group the transactions for, let's say, 1 hour or 1 day into blocks. What that would mean is, let's say the first set of 200 transactions that came in the first 2 hours of the bank activity, they are added together and put into a block. And once that block is formed, we keep it aside and we start the new block for the rest of the transactions that are going to come in after the last transaction that came in for the previous block. So what we've done is we start adding these transactions together, and the moment a time of one block expires, we create a new block. So what we've got is a set of blocks that represent a group of transactions that have been made over a period of certain time. So this structure is essentially what blockchains propose. Now, obviously, if we group all our transactions this way, we still don't solve the problem of trust or the problem of someone damaging this data or this data getting destroyed. Just because we have formed blocks doesn't really mean anything. Once we are able to group these blocks together, one thing that we do is we convert these blocks into hashes. What this hash means is that we convert all of the data that's there in a block into a filtered sequence of alphanumeric string. And before we get into what that means, let's just assume a block to represent a hash as a unique identifier of that block. And that unique identifier essentially depends on all the data that's there in the block. And one simple assumption that we have to make is that the moment a data element is changed in the block, this hash also changes. We will study digital hashes in detail in our coming sections, but before that, let's just assume that a simple identifier that represents the block data is calculated, which represents the hash of the block. Now, our proposition is simple. Every time we create a block, we create a hash of that block also. And every time we create the next block, as a part of the data in the next block, we add the hash of the previous block also. Now let's look at this in a little bit of detail. What we have is a sequence of blocks which are the grouping of the transactions, and what we've said is that each block is going to carry the hash of the previous block along with all of the data, which is essentially all the transactions that a specific block has. So we've got the first block which has a certain hash which we've carried forward into the next block, which also has another hash that's carried forward to the next one. So this sequence of blocks, they start depending on the previous block as they get stacked one on top of the other. Now this simple sequencing of blocks with one block linking itself to the previous block using hashes is what makes blockchains immutable or tamper proof. The question to ask is, how does this happen? So every time I add a new block, what I'm doing is I'm calculating the hash of the previous block and adding it to this new block that I'm adding on the stack. And the way those transactions get entered, I will have the latest block on which I'm going to have some data and the previous block's hash. Now imagine someone tampers the block of 3 sequence back, or the block 3 in a 6 block transaction set or a 6 block data set. What will happen is, when someone tampers the data of block 3, then the hash of that block is also going to change, and we'll talk about how hashes work and how hashes change. But what that will do is it will change the data of the next block. The reason for that is that the entry hash that we are adding of the previous block is going to be changed accordingly. This change is going to cascade itself to the top of the blockchain or the top of the chain of blocks. This is what's important. Now, since this hash has been changed, all of the data of hashes that are calculated subsequent to this change are also going to be changed. And what we'll finally notice is that if there is a tampering that's executed, then the final hash is going to be changed compared to what the honest chain of blocks had. And it's very easy to compare hashes and detect this tampering. Not going in further detail on how this hashing is implemented, let's assume that this hashing scheme ensures that data is tamper proof and corruption free. With that assumption in mind, what we've done is taken the first step towards trying to understand how blockchains can replace a trusted data ledger. With that, let's come to the step where we define blockchains to a certain extent. So there are multiple definitions that one could look at, and it's very easy to confuse oneself depending on what level of awareness one already has. The simplest definition is related to blockchain's utility, which is blockchain is a trusted record keeping technology. It's fair to assume that when we're talking about banks and financial data, we need trust. And if we're trying to replace the technology underlying that record keeping, then it obviously needs to be trusted. So that's what blockchains are. They are trusted record keeping technology. Another definition that one would find is blockchain is a distributed, decentralized public ledger. Now, what distributed or decentralized means is something we will get to. But one of the things that needs to be understood is that blockchains ensure that data is not stolen or data is not damaged. And how that's done or how that's achieved is by distributing blockchains to different nodes or different parts of the network so that a copy is always maintained. This redundancy ensures non-destructibility, which is what's represented in this definition. Some of the other definitions relate to incorruptibility of data, which is the result of what we've just seen, and how different stakeholders who want to update data cannot be called on to make that update without being a part of a consensus mechanism, which is something that we will take a look at. What we finally understand is they are immutable digital ledgers that can be securely used to record transactions that are taking place in a given network, in our case a bank. Once the data is sealed within a block, which is what we just saw, then it cannot be changed retroactively. No one can change historical data on the blockchain. With that high-level introduction, we get some idea of the relevance of blockchain technology. One of the things that we have to understand is blockchains are not a revolution. They are not a completely new innovation. One thing that we saw was the usage of digital hashes. Digital hashes have existed in blockchains much before blockchains were conceptualized. Similarly, digital signatures or decentralized distributed networks, these have existed much before blockchains were ever thought of. To understand blockchains, one needs to just be familiar with these three basic technologies so that one can understand how they come together and create this trusted ledger system that we've been talking about. These three technologies are crypto hashes, digital signatures, and peer-to-peer networks. Our objective is to understand how these three very diverse but legacy technologies can be innovatively combined to form something called a chain of blocks or digital ledger or trusted computing system called blockchains. With that, we've got a high-level introduction of what blockchains mean and what are its building blocks. We will expand on all of these different elements of blockchain technology. We will study them individually and we will see how they combine together to create blockchains. Thank you.